Hello, folks. We are going to do section 3-3 today. 3-3 is titled Graphs of Nonlinear Inequalities. It really is kind of a nonlinear inequality catch-all. We're going to be doing some graphing of nonlinear inequalities, like it says, but we're also going to be solving just regular inequalities, absolute value inequalities more specifically, because these are things, it's kind of a nice review before we go on and do some other things, but we will be doing some absolute value inequality solving also. That's why I wrote that in the title, as you'll see in a moment, as we go over to the notebook. Graphs of nonlinear inequalities and solving absolute value inequalities. That's really the both things we're going to be doing. So first off, I'm just going to jump right into one of the most basic examples, just to see if we understand what an inequality is. And they'll say this, they'll ask you, determine whether let's say -2,6 is a solution for, let's do this one, y greater than x plus 2 squared plus 3. So how would I determine whether ordered pair, this point, is a solution to this inequality? The easiest way is just plug it in, right? This is my x, this is my y, so I plug it in here. 6 greater than -2 plus 2 squared plus 3, right? I end up with 6 greater than, this is 0, 3. Is 6 greater than 3? Yes. It is a solution. Is a single word now. Did you know that? And it looks like it the way I wrote it. All right, so yes, it's a solution. You just plug it in, check and see, does it make the inequality true, right? All right, so that's the most basic. I don't think many of you are going to have trouble with that. What I'm going to look at with you today are ones where they ask you to graph. And they'll say graph, let's do this one, y less than or equal to 2 times x minus 1. So I'm going to graph this. You got to think about how we graphed the boundary, right? We always went to the boundary first. First step is realizing we're graphing y equals 2 times the absolute value of x minus 1. What do we know about this graph? We know it's shifting right 1, and we also know that it's going to have a multiplier, a vertical, I guess a vertical expansion by a factor of 2, right? It's going to go up faster. So what is this going to look like? Well, it's going to move right 1, so it's going to start here. And it's going to go up by 2 each direction. So it's going to keep doing that. So it's going to look like this. Now, I look at this also. I'm going to stop here for a second. I'll go back to that. I look at this sign. The second thing I have to decide, dotted or solid, right? Just like we did before with linear inequalities. Same idea. So now I'm going to draw this. This is solid because this one is a less than or equal to. So it's going to go there, and then it's going to go there. We're going to have that graph. We've got the boundary drawn. Now we have to decide, the last thing is shading, right? And the way we figure out shading is looking at the original inequality. If I take a representative point from one side or the other, remember, this is, instead of like where it was a line, it was one side or the other, this is kind of inside or outside. So we're going to either go inside or outside and figure out, because all the solutions are either in here or all of them are out here. So I like to try 0, 0, as you're well aware if you've been paying attention. I like to plug that in as my test point. So if I do that, I'd have 0 less than or equal to 2 times absolute value of -1. So that's just 0 less than or equal to 2, right? Is that true? Absolutely. So we're going to shade everything out here. All right. There's one example. Let me do this. All right, now let's go do another. Let's do this one. All right, y is less than the square root of x minus 2 plus 1. So what is this going to look like? Again, y equals square root of x minus 2 plus 1. So this is the square root graph. That's that root ramp. Remember, it says only positive, so we're not graphing both positive and negative, just the positive root ramp, x minus 2. So that, if you remember, starts at 1, at 0, 0, goes to 1, 1, goes from 4 to 2, right? That's the basic graph of this function. At 1, 1, we have a point. At 0, 0, we have a point. So it's that root ramp that does this, right? That's what that graph looks like. But this is going to be shifted right 2 and up 1. So normally where we'd start here, we're going to go right 2 and up 1. We're going to start here now. It has nothing that's changing, transforming its shape, stretching it either vertically or horizontally. So we're just going to go over 1 and up 1, over 4 and up 2, and then we have to decide how to draw our line. This tells me I have a dotted line. So I am going to draw this as a dotted line. Let me do this. I'll do that, and then I will do that and see if I get something I want. Oh, it is allowing me to do that. Beautiful. So I'll get this, right? That's my graph. So now I have to decide shading. You have to be careful with these root ramps, all right? Anything below this value of 2, like 1, 0, anything on this side of this is not part of the domain of this function. So any shading I do has to start at 2 and go this way. Start at 2, go this way. Don't go this direction at all. All right. In fact, I don't even like how my point looks like it's more that way. That's our point, right? Anything this way, above or below, is going to be what we shade. So I test it. I use 0, 0 again. If I use 0, 0 in the original one, I get 0 less than the square root of, oh, I can't use 0, 0, can I? It's not in the domain. I just said that. All right, so we can't use what I normally use. I got to pick another point. So I'm going to pick a point like 4, 0. 4, 0 is obviously below this rather than above it. So if I use the point 4, 0, I'm going to have 0 less than square root of 2 plus 1. Is 0 less than 1 plus root 2? Well, root 2 is, I think, 1.414, so this is 2.414 approximately. So that would be true, wouldn't it? 0 is less than this. So we would want anything below this. And so that's going to be, whoa, I just did what I said don't do. Don't go to that side. I just slipped because I'm using a tablet that is very tricky sometimes to draw straight lines on. All right, there we go. So everything below that, that is our solution set. So again, draw the boundary, draw the line, whether it's dotted or shaded, right? Or I should say dashed or shaded, I guess, and then shade one side or the other. Let's do one more. Let's see, do that. All right, now let's use a different color. Let's do y is greater than or equal to x plus 3 cubed. All right, so again, we're going to do y equals x plus 3 cubed. And x plus 3 cubed is the normal cubic graph, which, again, just to review, goes over 1 and up 1. All right, over 1, up 1. Over 2 would go up 8. It's going to be way up here, so it goes up very quickly from there, right? And the same thing on the back side. It goes through 1, 1, or -1, -1, and goes down very quickly. So what do we have? It's shifted left 3. So we're going to go left 3. We make our center. And then this is go over 1 and up 1, over 2 and up 1, 2, 3, 4, 5, 6, 7, 8. Right? Back 1, down 1. Back 2, down 2, 4, 6, 8. So we'll have something like this. This is going to be a solid line. Whoa, and wavy because I'm drawing again. I got to get used to drawing on this. It'll get better. So we're going to have that. And now I have to decide shading. Well, again, this side or that side. So I'm going to pick 0, 0 because I can. 0 greater than or equal to 3 cubed. Is 0 greater than or equal to 27? I would say no, right? Using 0, 0 is, again, just so you know what I used. So that is not true. not greater than. So this is not the side with solutions. This is the side with the solutions. And that's it. That's what we're doing with the graphs, all right? Now, the part of this thing, this section that they don't even mention in the title, they just kind of throw it in there on you, is this idea of solve and given an inequality, an absolute value inequality. So again, I know you guys have had some experience with these, but I want to revisit this because I don't know if you've ever really had a good experience with absolute values. All right, we need to solve this. But in order to solve this, I got to talk about something else first. Over here, I want to just look at something. If I asked you to define for me what it means when x is, the absolute value of x is less than or equal to, say, anything, let's say 4. Absolute value of x less than or equal to 4. What does that mean? What that means is that we want the set of all x's that are a distance less than 4 from 0. All right, this is a distance solution, so to speak. When I have this x in an absolute value, I want all the values that would make this true that are a distance of 4 or less, because it includes 4 because of the greater, less than or equal to, 4 or less from 0. So on a number line, that would look like this. If I had 0, -4, and 4, it would start here with a solid dot because it includes 4, and it would go this direction. But it would also distance, I'm sorry, it's less than 4. Hello. Twice I'm getting distracted here. All right. And everything this way, right? Less than. But at the same time, a distance less than 4 to 0 would be here, but it's also coming from this side. This is a distance, even though it goes to -4, it's a distance of 4 or less with everything in here. So it'd be coming this way. So really we have everything that overlaps, everything that makes both of these true, a distance of 4 or less from 0. So how do we say that without the absolute value? And this is what I call interpreting the absolute value. What this means when we have less than, this is just for less than. All right, if we have a less than or equal to, I'm going to put this x less than or equal to 4 and greater than or equal to -4. We say this as an and statement, meaning it makes both things true. X is less than or equal to 4 and greater than or equal to -4. That gives you all those x's that are a distance of 4 or less from 0. All right, so if that's less than, what does greater than look like? Well, again, for the same idea, if I have absolute value of x greater than, I'll just do strictly greater than 4. What that means is that same thing on the number line, everything from 4 out, I'm going to do an open circle this time and go that way like I tried to last time. And open circle, go that way, right? These are two separate groups. There's no way you can say and. There's nothing that would make it true. This is an or statement. It's this set or this set, where this one, it has to make both true. To be a distance greater than 4, it's actually two disparate sets, two that don't share any members. So we write that as that. We write this one as x is less than -4, and then we have to write this word, or, because if you just put a comma and write the next one, it doesn't mean the same thing. You have to write or, x greater than 4. Though that describes the set of values that we want from the number line, just like this describes that set for a less than. All right, so less than, greater than, this is how they work. So we have to look, when we get this solved and they give us this type of thing, value, same thing. Even though it's more, there's an expression in here rather than just x, we do the same thing. It's a less than. Less than means and. It means I put these in between the two pieces. So I do this, 6, and then I go greater than over here, and -6. I do the opposite. All right. Now I solve. I solve for x to get x by itself. I'm trying to, in here, get x by itself. So I'm going to add 10. When I say add 10, I do it to all three things. So over here, -6 plus 10 is 4. Here, this thing cancels the 10 there. X less 6 plus 10 is 16. Almost got x by itself. I got to get rid of x, or the 4 in front of the x, so I divide by 4. When I divide by 4, remember if you do, well, we'll get to divide by negative. Divide by 4. When I divide by 4, whoa, how did I do that? I don't want that. All right, let's try doing what I really wanted. All right, So dividing by 4, what happens? Divide this by 4, I get 1. Divide this, I get x. Divide the last part, I get 4. This is my solution. That means x greater than or equal to 1, less than or equal to 4. I don't think they ask you to do a number line, but on a number line, if it helps you to see it, if this is 4, this is 1, this is 0, it would be closed circle, everything between these two. And again, I don't think they ask you to do the number line. I just show you that to illustrate what set of values it means. We get x by itself that way. All right, let's do another one. Let's do a greater than. So again, solve are your directions. And it's going to be absolute value of x plus 5 plus 2 greater than 6. One thing I didn't mention before is the other ones had the absolute value isolated already. It's not here, so we have to do that. We have to get rid of everything else on this side. So I want absolute value of x plus 5, and that's going to be greater than 4. If you don't do this, you won't get the right answer. You got to get rid of everything else first. Isolate that absolute value first. All right? So isolate it. Now we eliminate it. We interpret it. So this is a greater than. That means this statement has to be, it's greater than 4, so it has to also at the same time be less than or equal to negative 4, right? Greater than, I'm sorry, not less than or equal to, just less than. You do the opposite sign, opposite value. Now, you say or, I always write it here so you remind yourself there's an or in here. And then you write exactly what you see, x plus 5 greater than 4. All right, so you do the opposite of the symbol, opposite of that value with the x plus 5 that's in there. Then you do the same thing you see there with the x plus 5. Now we solve each of these individually. All right, so what we're going to do next, I'm going to, whoa, did it again. I'm going to subtract 5 for both sides. I get x is less than negative 9. Or, and again, I try to write this just to keep reminding myself. Negative 5 on each side here, I get x is greater than negative 1. So we write this just like this. Honestly, I don't even have to rewrite it. It's there. All right. What would that look like on a number line? Again, I show this just to illustrate. If this was negative 9 and this was negative 1, 0 there, x less than negative 9 would be open circle going that way, greater than 1. Negative 1, open circle going that way. That would be our solution sets, two separate sets that combine with the or. All right, either here or there. All right, one last example. Absolute value of negative 2x plus 2. And that is going to be less than 7. All right, so what do we got here? We have a less than. I'm going to rewrite this. I'm going to interpret that absolute value. It's already isolated, so I don't have to worry about that. Actually, I missed part of the problem, and I do have to worry about that. Sorry, guys. That's in too much of a hurry. Minus 1 is less than 7. So we do have to do this first. Always do that first, just a reminder. Now we'd have negative 2x plus 2, the absolute value of that quantity, less than 8, right? Adding 1 to each side. So now what we have to do is interpret this. Negative 2x plus 2 less than 8. Well, this is an and statement, so I just go, why do I want to keep putting that under there? We do the other sign over here, and we do the opposite value, right? So it's between negative 8 and 8. Whatever's in this absolute value is between these two, it and its opposite. So we have this. All right, so what do I do? Well, I got to subtract 2 from everything. So this is negative 10, less than negative 2x, less than, subtracting 2, 6. All right, now I have to divide. I'm dividing by a negative 2. This is where, if you remember, when you have these greater than or less than, when you divide by a negative with an inequality, you have to switch signs. You have to flip them. There's an easier way to do it. Instead of flipping the sign on this long statement like this, you can just flip the endpoints. When I divide 6 by negative 2, I get negative 3. Put it over here. Have the same sign. When I divide negative 10 by negative 2, I get positive 5. See how that keeps the right relationship? The bigger number is here, the negative number is here. And then this stays where it was at. That's x. And we've got our solution. So again, when you divide by a negative, you have to flip the symbols. And that makes this. And the reason I say to do that is because if you wrote this by just going directly in here and going 5 is greater than X is greater than 3, this is not a good mathematical statement. We never go from greatest and down. All right. You have to, if you wrote this first, and you're welcome to do that, you have to turn this around and start from the smallest. I'm sorry, that would have been a negative 3. You would go from the smallest. So you would have to flip it around and make it look like this anyways. All right. I want to be clear on that. I thought that was going to be my last example. I want to give you one more because there's some in here that will say this. All right. Something like absolute value of 3x is less than negative 1. If I ever get to this point, what do I say? And I could even have something in here if I have plus 2. Before I even start this, this is telling me an absolute value less than negative 1. Is that possible? I don't think we can do that, right? This would always come out positive. There's no way a positive value could be less than negative 1. So right here, right from the get-go, I can just say no solution. And I'm done. And this time I really mean I'm done. We don't have any more examples. That's what we're doing, guys. All right, so have at it, and I will talk to you tomorrow. Have a great night. Bye. Having trouble stopping the recording.